Hi guys, lesson 2 on electromagnetic waves, and in this one I really want to focus on the idea that electromagnetic waves or light waves are waves in the fullest sense of the word, and that means they obey all wave properties, and they obey all wave equations. An example of a wave equation which you saw already is that the speed of a wave equals wavelengths times frequency, and that of course is true. Just one thing to remember, that electromagnetic waves or light waves always travel at this one specific speed in vacuum, which is 3 times 10 to the 8 meters per second. But pretty much everything else we know about waves is also true. For example, we know that when waves hit a boundary of some kind, they reflect, and you know that because you've looked in a mirror. We know that when waves hit a different medium, they're going to some of it will go through and some of it will go back, and that you know because you've been able to look through a pane of glass and you've seen that light actually go through that pane of glass. And you also know that some other equations we've used in the past about waves, for example, speed equals distance over time, and the equation for the Doppler effect, which tells you that the observed frequency of a wave is equal to this complicated thing, which is the speed of the waves plus or minus the speed of the observer over the speed of the waves minus or plus the speed of the source times the emit source frequency. These are all also true for electromagnetic waves. Let's see a couple of cases of how these work. Okay, one example of how we can keep using these equations for electromagnetic waves is, let's say we think about the light that's going from the sun to the earth, and let's see how long it takes a particular photon, that's a particle of light, to travel from the sun to the earth. So look on your reference table, find the distance from the earth to the sun. That distance is going to be 1.5 times 10 to the 11 meters. And we're going to say that the light is going to travel more or less in vacuum. Yeah, there's not really anything in space until you get very close to the Earth. So what equation would we use here to find the time it takes the light to go to Earth? Well, we'll just use our favorite equation, speed equals distance over time, and rearrange this equation for time. So time is going to be the distance divided by the speed of the light. So that's 1.5 times 10 to the 11 meters. Divided by 3.0 times 10 to the 8 meters per second. And if you calculate that, you're going to get an answer in seconds, which is exactly 500 seconds. Converting this into minutes, we'll say that 1 minute equals 60 seconds, or we're not going to say that, that's just what it is. And there you get the familiar result of it taking about 8 minutes, or more precisely, 8.3 minutes for light to travel from the sun to the earth. So if the sun just blew up right now, you'll find out in about 8 minutes from now. Another example you'll see quite often if you're interested in astronomy of how the electromagnetic waves obey all wave properties is that of the red shift or the blue shift. So that's basically a consequence of the Doppler effect. Let's imagine we have an astronomer on Earth, and he's observing the light coming from a faraway star. Well, let's say this red star is emitting light that is what appears to be red to him, or redder than he would expect it to be based on the chemical composition. What can he conclude about that? He can conclude that if the frequency that he observes, if the frequency observed is less than the frequency emitted by the star, then that means the star is moving away, the star is receding. And we call that a redshift. The reason we call that a redshift is because if you remember our spectrum, there's the visible light right in the middle, and in that visible light, red light and blue light, we're kind of at the opposite ends of the visible light spectrum. In fact, remember the red light had the longer wavelength, so that meant it had the lower frequency. So that's why we call a receding star, one with a smaller observed frequency, a redshift. And if we have a higher frequency or a shorter wavelength, then we would call that a blue shift. And that would mean, of course, that the star is going towards you. Why do we call it a blue shift instead of a violet shift? Good question. I don't know, but we call it a blue shift. You guys are going to get a few sets of problems from the sub about redshift and blue shift and various electromagnetic wave properties. Please note you probably will have to look up the Doppler effect equation in your notes. I hope you have your notebooks. All right, good luck with the problems, everybody.